Good morning. Today's video is the continuity of the previous video in which I was explaining chapter 1. This part is actually called photospectrometry. It deals with measuring the transmittance or absorbance of light when it passes through a given sample, mainly to calculate its concentration. What is the advantage of using photospectrometry? Photospectrometry is one of the methods used to determine the concentration of a certain sample by studying the absorbance or the transmission of light passing through the sample, and for sure for monitoring the change in the concentration of the sample as function of time if there is a chemical reaction taking place. Spectroscopy is a very reliable method in determining the concentration of samples. Spectroscopy means the study of how light interacts with matter. All molecules absorb and emit light differently based on what kind of covalent bond they have in them. This is done using an instrument called photospectrometer. The photospectrometer gives us data in the form of an absorption spectrum, which displays how much light through a band of frequencies is able to pass through a sample to reach the detector. We look at the spectrum, which is presented as a graph where we plot on the ordinate axis. We usually plot the absorption, transmittance, or the absorbance, and on the abscissa the wavelength, the frequency, or the wave number of the incident light on the sample. So we look at our spectrum, and if we have an absorption spectrum, for example, we look at the peaks. So where there are peaks, it means that not much of the light of that wavelength or that frequency is getting to the detector, which means that it is being absorbed by the sample. If we collect data as function of time continuously over the duration of the chemical reaction, we can gather information about how rapidly the absorbance is changing or how rapidly the concentration of a certain substance is changing over time inside the sample. So I will draw a figure showing how an absorption spectrum would look like. So this is the ordinate axis, this is the abscissas axis. On the ordinate axis, we can do the absorbance if we are drawing an absorption spectrum or the absorption. I will explain the absorption. And on the abscissas, we can do the wavelength, the frequency, or the wave number of the light that is being incident on the sample. And such sort of spectrum would be like this, for example, with different amplitude. So we can understand that high absorption occurs here at a certain wavelength, and another absorption occurs here at a second wavelength. So this is called an absorption spectrum, for example. So how is absorption known? By measuring how much light reaches the detector, we may know at what wavelength the light is being absorbed. يعني بمعنى آخر لنرسم الابsorption spectrum بنبعت ضوء. هالضوء بيروح لعند السامبل. it may be monochromatic, polychromatic، يعني في كذا frequency. أكيد إذا أنا بدي أعمل plot لازم يكون polychromatic. في يكون كمان monochromatic. so إذا نحن عم نبعت ضوء بنشوف هيدا الضوء قد عم يعمل absorption على أي wavelength. كيف بنعرف وين عم يعمل absorption؟ من transmitted intensity أو من transmitted light اللي قطع لتاني جهة. بنشوف مين قطع، قد الكمية اللي قطعت مقابل الكمية اللي كانت عم تنعطى، فبنقدر نعرف مين اللي انعمل له absorption، وهيك بنعرف ال quantity اللي انعمل لها absorption. وهيدي quantity is related to the concentration of molecules that are found inside the sample. So when absorption increases, it means that the concentration of the molecules inside our sample increases. They are related together. We will see how by a law called Beer-Lambert. So what is this spectroscopy about? This spectroscopy talks again about the interaction of a light with a sample. This light has an incident intensity, let's call it I0, at a certain wavelength lambda. It crosses a sample. The molecules of this sample will absorb a part of this light, another part will be, the rest will be transmitted with an intensity I, so I is the transmitted intensity. And for sure there is a part which is absorbed by the molecules of the sample. So we may define some terms. Let's define the absorption. What is the absorption? It is the quantity absorbed, the intensity absorbed, or the ratio of the intensity absorbed to the incident intensity. So it's simply A, it's equal to I0 minus I. So I0 is the incident, I is the transmitted. We get I0 minus I is the absorbed intensity over I0, which is the ratio of the absorbed intensity by the incident intensity. If you would like it to be as a percentage, we multiply it by 100 and we will get it as a percentage. Otherwise, it will be a number between 0 and 1. The absorbance. The absorbance is defined as A equals log I of I0 over I. So I0 again is the incident intensity and I is the transmitted intensity. So you can see that I0 and I have the same unit. So for sure I0 over I has no unit. So either we can say that A has no unit, or sometimes in some books it's expressed in UA or unit absorbance. Both are correct. We can either consider it unitless or take UA as a common unit for the absorbance. So this is the absorbance. Let's go to the transmission. The transmission is defined as I over I0. I is the transmitted intensity and I0 is the incident intensity. So this ratio I over I0 is the transmission. It will give me a number between 0 and 1. If multiplied by 100, it will be a percentage. It's usually given as a percentage to give the percentage of the transmitted light through a given sample. So it's clear that there's a relation between the absorbance and the transmission. You can see that A, so A is equal to log I0 over I. So we can say it's equal to log 1 over T, because T is I over I0. We just multiply by 100 to give it the form of a percentage, and it can be equal to minus log T. So this is the relation between the absorbance and the transmittance. And why use the absorbance instead of using the absorption, or why define the absorbance? Because they have found that this term, the absorbance or the log relation itself, the log of I0 over I, is related to the concentration of the sample directly. So instead of using complicated forms, they have found that using the absorbance in this form is really helpful in defining an easy equation that we can make benefit of and find the concentration of the sample we are dealing with. Now let's look what happens to the absorbance if we mix two substances X and Y of concentration Cx and Cy together in the same solution. First, let's consider them separated. So let's consider solutions X and Y with concentrations Cx and Cy respectively, each of them in a separate container, as you can see here. So a light beam with incident intensity I0 crosses the first solution X, which contains substance X with concentration Cx, and then I1 is the transmitted light from the first solution, which is going to be incident on the other solution Y, which contains substance Y with concentration Cy. I2 is the transmitted light from the second solution. Now, let's prepare one solution that contains the same substances X and Y with the same concentration Cx and Cy, the same incident intensity must give the same final transmitted intensity of light as in the previous case, because they are the same molecules, so the same absorption must take place. So the same intensity of transmitted light must be observed or detected. يعني شي طبيعي إذا كان الانسيدنت لايت هو ذاته فوق وتحت يكون transmitted light هو ذاته فوق وتحت، لأنه هن نفس الموليكولز اللي عم يعملوا absorption، نفس الكمية اللي عم تعمل absorption فوق وتحت، إن كانوا كل وحدة بكونتينر لحال أو كانوا مع بعض بنفس الكونتينر. So I0 will give final intensity I2, same I0 will give the same final intensity I2. Remember, we are interested in the absorbance of the mixture. So as it says the title, addition of absorbance. So we're interested in the absorbance. Let's try to calculate the absorbance in both cases, where they are placed in series and where they are mixed together. In the first case, where they are placed in series one after the other, so we can find T1, which is I1 over I0. I1 is the intensity of light transmitted through the first solution. I0 is the incident light. And T2 is equal to I2 over I1, where I2 is the transmitted light from the solution 2, where I1 is the incident light on solution 2. Now, for the second case, where we mix them together, the transmittance is simply the final transmitted intensity over the initial incident intensity, which is I2 over I0, which is I2 over I0, as you can see here. So we can simply insert the term I1, which will give us T1 times T2, where T1 and T2 are the transmittance of the solutions 1 and 2 respectively of the first case for sure. So a simple calculation will give us A, the absorbance of our case, of this case, where they are mixed together, equals minus log T. T is the transmittance or the transmission. T is equal to minus log T1 and T2, where T1 and T2 are the transmittance of the individual solutions. Distribute the log, or it's minus log T1 plus minus log T2. Minus log T1 is A1, the absorbance of solution 1, and minus log T2 is A2, the absorbance of solution 2. So this is solution 1 and this is solution 2. So we arrive to a conclusion that says the absorbance of a mixture of substances is equal to the addition of individual absorbances of these substances. Now let's see how studying absorbance or absorption or transmittance through spectrophotometry can make sense in calculating the concentration of a sample. This is done using a law called Beer-Lambert, or simply Beer's law. Beer's law gives a relation between the absorbance and the concentration. It's a simple relation, it's a clear relation, as you can see it, A equals epsilon times L times T. So let's see what is this relation. A is the absorbance of the substance we're talking about, which is found inside a certain solution. Epsilon is the molar absorption coefficient or molar absorptivity measured in liter centimeter minus 1 mole minus 1. Epsilon gives an idea about how much light does a certain substance absorbs at a certain wavelength. So epsilon is a characteristic of the substance and also at a certain wavelength. So if we change the type of light, for sure the absorption or the molar absorption will change. L is the light path through the solution, which is in centimeter. So for sure, absorption must be proportional to L, because as the beaker or the container gets wider, for sure the absorption must increase. So this is logical. And C, at last, is the concentration of the solution we're talking about in mole per liter. For sure, if C increases, the absorption must also increase, which is also logical, because more molecules will be present in the solution and the absorption must for sure increase. I have to give a small hint that this law, Beer's law, is only applied for small concentrations or for solutions with small concentrations. At large concentrations, this law will be no more valid. Nevertheless, it gives very reliable answers in many applications all over science. There's another form of Beer's law beside this one. It can be written in this form, so let's take a look. We know A equals epsilon LC, where A is equal to log I0 over I is the incident and I is the transmitted intensity, epsilon LC. Let's do I0 over I equals 10 epsilon LC. So we can write I in terms of I0, so it will be like this, I equals I0 over 10 epsilon LC, or it can be written like I0 10 minus epsilon C, or we can write it like this I0 10 minus A. So this is the relation, or Beer's relation, that relates the transmitted intensity to the incident intensity in terms of the absorbance. So it's clear. The final version of Beer's law, or a generalization to Beer's law, if we have more than one substance in our solution, A for our solution at a certain wavelength lambda, it's equal to L times summation over I are the substances that are found in a solution. Epsilon I is the absorptivity of the substance at this certain wavelength inside the solution, and Ci is the concentration of this substance inside the solution. For sure, we have already shown that if we have a mixture of substances, then the absorbances add together. So if we have a mixture of substances, A is equal to the summation of AI. And if they are all found in the same, so it's Li, epsilon I, Ci, because they are all found in the same container, so they have the same L. So it's the same L. L goes outside the summation, and there remains Ci, epsilon I, Ci, where epsilon I is the absorptivity of substance I in the solution, and Ci is its concentration. So this is the generalization of Beer's law. Now let's do an exercise. Exercise says irradiation having a wavelength of 280 nanometer goes through a 1 millimeter thick aqueous solutions of tryptophan amino acid that has a concentration of 0.49 millimole decimeter minus 3. The intensity of the radiation beam is reduced to 52% of its initial value. Calculate the absorbance and the molar absorption coefficient of the solution at 280 nanometer. Before understanding the solution, let's just understand the given. So what is this? This is the wavelength of the incident light. This is the thickness of the container that contains the sample we are studying. So this is L. And this is the concentration, which is C. The concentration is given in a different unit. It's not in mole per liter, but it's okay. We shall keep it with the same unit it's given in. The intensity of the radiation beam is reduced to 52% of its initial value. This means that I transmitted over I0 is equal to 52%. So it's equal to 0.52. So now let's start solving. He needs the absorbance A. So because we have the transmittance, this is the transmittance, there's a direct relation between the absorbance and the transmittance. A equals minus log T. So we just substitute the value of the absorbance, 0.52, and we get our answer. We are searching now for the molar absorption coefficient, or the molar absorptivity, epsilon. And how to find it? Using Beer's law. So A equals epsilon CL. We are searching for epsilon. Epsilon equals A over, so implies epsilon equals A over CL. A is already calculated previously, it's minus log 0.52. C is given, I've changed it to mole decimeter per decimeter cube. So I've just multiplied by 10 to the power minus 3 to change from millimole to mole. And I've changed the thickness to the usual unit, which is centimeter. It's usually used in centimeters. So it's 0.1 centimeter. So this one has no unit. This one, I will keep it in the same unit, it's okay, but just change from millimole to mole. And the millimeter is changed to centimeter. And at last, calculate everything. We will get 5.8 times 10 to the power 3. I've kept the same unit, so it's here it remains as decimeter cube, mole minus 1, and centimeter minus 1. So this part here comes from the concentration, so I'll keep it the same. We don't care. Now, in the second part, determine the transmittance through a cell of the solution of 3 millimeter thickness. He's asking me to find the transmittance A. Transmittance means I have to find A. And he's giving me the thickness. He's giving me L, or let's call it L prime. He's giving me L prime, and he's asking me to find the transmittance. Transmittance is related to the thickness, because we have said that when the thickness increases, the transmittance will increase for sure. When the concentration increases, the transmittance will also increase. But epsilon is a characteristic to the substance. It doesn't change. And same substance, whatever the concentration of this substance, whatever the thickness of the container, it will always have the same epsilon. So epsilon does not change. It always remains the same. For a certain substance, for a certain substance at a certain wavelength. يعني هي كأنها characteristic ما بتتغير حتى لو تغير الكونسنتريشن. يعني هيدي المادة بتمتص على هيدي الويف لينث هاي كمية. اوكي سو هي constant، يعني لهيدي المادة الأبسون عندها هالقد ما بتتغير، يمكن كتار أو شوي، كبير صغير البيكر ما بتتغير الأبسون. Epsilon is constant always. So once we find it, it doesn't change. But if we change L, A will change. Okay. So if we are keeping the same concentration and we're changing the thickness of the beaker، يعني غيرنا بس البيكر اللي هن موجودين فيه صار thick، أكيد الابسوربنس will change، يعني قد ايه رح يمتص الضوء، لأنه أكيد رح يقطع الضوء بمسافة أطول، فأكيد رح يصير في امتصاص أكبر للضوء، هذا شيء طبيعي. So how to find A, or let's call it A prime. A prime equals epsilon, doesn't change. C, you have kept the same concentration, and we have a new thickness of the beaker. So just substitute. So epsilon already found here. I've kept the same unit. So C is the same as before, did not change. So you can see the unit of the concentration will be directly deleted. So no need to worry about it. And now L is 0.3. I've placed it in centimeter, which is the usual unit for the thickness. Multiply all of this together, you will get the absorbance, and remember that the absorbance has no units, or we can put it in unit absorbance. And at last, we want to find the transmittance. A simple relation between the transmittance and the absorbance is T equals 10 to the power minus A. Where does this come from? From this relation. So this relation gives us A equals minus log T. So it's clear that minus A equals log T, and 10 to the power minus A is equal to T. So, or you can, as you know, it's 10 log T. So this will be cancelled. We will get T equals 10 minus A. Calculated, you'll get 0.14. And this is the end of this exercise.